Section 6.2, another application of diagonalization and eigenvalues and all that is in differential equations. Okay, so we want to look at this idea with differential equations. And so they just they point out that, okay, I could have dx dt, I'm going to call it x prime, equals ax plus by. This is what we call a homogeneous system because this is x is a function of t, y is a function of t, but I don't see any t's in there anywhere. And then cx plus dy. Right, so again, we've got x of t and y of t. And then a, b, c, and d are just constants. And so I could write this as x prime, y prime as a single matrix equation. And then a, b, c, d times x and y of t. Okay, so if we generically call x, y the vector x, and they say, well, there's x dot, that's one way to talk about derivatives. I could use a prime, they use the dot, times a, and then our vector x. Okay, so okay, that's what we have there. Then if we substitute, so the idea here is, now we've found P such that and in this case they're going with distinct eigenvalues and so forth, right? So such that P inverse a P is equal to lambda 1, 0, 0, lambda 2. Okay, so we have that. And so then they say, well, substitute our x vector with py. And now they tell us y is some x1, y1 of t. Okay, so we're making that substitution. And so that is actually then P times the vector y dot. Okay, now you might have to think about that a little bit, right? You know, so what this is saying is if I have x, you know, so I have x, y is equal to some p11, p12, p21, p22 times x1, y1. That means that, and I'll just look at the x here, x is equal to p11 x1 plus p12 y1. Now when I take the derivative, x prime equals, well, these are constants, p11, so this is just x1 prime plus p12 y1 prime. So I can undo that back into the matrix form, and so that's how we're here. Okay, so we believe that, and this is all equal to, you know, ax, but that means it's equal to a p y. Whoops, big P like that, y. Okay, and so that means p y dot is equal to a p y. But now I can write this as y dot is equal to p inverse a p times y. Okay, but that's diagonalized, so y dot is equal to lambda 1, 0, 0, lambda 2 times y. But now you see that makes two simpler differential equations that are what we call uncoupled. This then is saying that x1 dot y1 dot is equal to our lambda 1, 0, 0, lambda 2 times x1, y1. But if we write that out, you see it's just saying x1 dot is equal to lambda 1 x1, and y1 dot is equal to lambda 2 y1. But both of these are pretty simple to solve because what you're saying is I have a function of t, right? I have the derivative of some function x1 of t dt is equal to a constant lambda, lambda 1 in this case, times the function itself. Okay, well, I know what kind of functions do that. That would mean, okay, that implies that x1 of t is equal to some constant, some other constant of integration, and I'm going to call it x0. That's just some constant in that case. E to the lambda 1 t. Right? You can take that derivative and see that it does satisfy that differential equation. And similarly, we have that y1 of t would be some constant y0 e to the lambda 2t. And so we're able to solve that very, very easily, right? And then we could transform back very easily to our functions, our original functions, x and x, x and y. I was going to say x of something, x of t, right? Because we know that, where is it? Here we go. There we go. There's our substitution. We know that x is equal to p times y. And so if I have the, if x was equal to p times y, then that means y is equal to p inverse x. And so I can get my initial values here, whatever we determine. I can get those in the correct coordinates, and then we're good to go, All right, so that's what they end up with. So let's look at an example doing that. This is example 6.2.3, and so they have x prime equals 2x minus 3y, and y prime is equal to 4x minus 5y, and we're also told that x of 0 is equal to 7, and y of 0 is equal to 13. And they go through, so our matrix is 2, -3, 4, and -5. Now, I'm not going to go through the characteristic polynomial and so forth. They just point out that we have lambda 1 is equal to -1 with x1 equal 1, 1. And lambda 2 is equal to -2, and with the corresponding eigenvector of 3, 4. Okay, so P is equal to 1, 1, 3, 4. And we know that P inverse AP is equal to -1, 0, 0, -2. Right, those are both negative. Yep. Okay. Okay, so when we make our substitution, that our y, so x is equal to py. What that then implies, right, is we get the diagonal system here. So we get x1 prime is equal to minus x1, and and y1 prime, yeah, they go to that dot notation. Y1 prime is equal to -2y1. Okay, so what we know is that x1 is equal to x sub 0 or x1 of 0. We'll do their thing, x1 of 0, e to the -t, okay, because I just used that -1 there. And our y1 is equal to y1 of 0, e to the -2t. Okay, but we also know that x1 of 0, y1 of 0, those coordinates, that is just our P inverse times x of 0, y of 0. So that's the initial conditions that we can do. Now the P inverse, I'm just taking their word for it, that it's 4, -3, -1, 1. And I am using the initial conditions of 7 and 13. And that tells us that we get -11 and 6. And so the solution to this thing is that x1 is equal to -11 e to the -t, and y1 is equal to 6 e to the negative 2t. And then, I need to, where'd it go? Ah, right there. Okay, so there are my solutions, but I need to multiply by p, and so I have that x, y is equal to p x1, y1, and so p was, what the heck was p? My memory just can't handle, 1314, okay, 1314, and this is times negative 11 e to the negative t and 6 e to the negative 2t. And so our final solution, x equals 1, so negative 11 e to the negative t, and then 3, so plus 18 e to the negative 2t, and y is 1, so again a negative 11 e to the negative t, and then 4 times that, so plus 24 e to the negative 2t. And so there's a solution to a differential equation done with the diagonalization, and pretty nifty.